Today we're going to create a simulation of the Rings of Power theme for the new Lord of the Rings series in Python. I'll put a link to a video in the description below where the creators of that theme describe how they actually made it, but I'll give a short summary now of how it works. Essentially, you have a vibrating metal plate and you put sand on it. And as the plate vibrates, sand will move around on that plate. Under almost all frequencies of vibration, the plate's going to be vibrating randomly, the sand's going to move around, and you're just going to get a shuffled mess. But at very particular frequencies of vibration, what happens is that you get a standing wave on the metal plate. What a standing wave means is that everything on the plate is oscillating together. Now, that doesn't mean the amplitude everywhere on the plate is equal. What it means is that the amplitude could be different everywhere, but everything is going up at the same time and everything is going down at the same time. What that also means is that there's locations on that plate where there's a minimum amplitude or even an amplitude of 0. So some places are going up and down, they're all going together, but if you fix the plate at the center, for example, so it's sort of suspended on a pole, resting on a pole, then nothing is going to be moving up or down in the center, and the sand will sort of move towards the center. Now, the beautiful thing about these standing modes is it's not just the center that isn't moving up or down. You get these beautiful patterns of locations where the plate isn't oscillating up or down, and the locations where there's no movement is where the sand is going to tend to settle in. What we'll do in this video is we'll create a 2D random walk simulation to simulate the sand moving around on the plate. And we'll show that over time, the sand tends to settle in these places where there's no oscillation. Before we check that out, I'm really excited to say that there's a new merchandise on this channel. For example, the beautiful new t-shirt you can see that I'm wearing here that has none other than Billy himself on the t-shirt. There's also a few other designs on the website as well, so be sure to check that out. And all the money that I earn from selling these t-shirts, I'm going to take half that and I'm going to donate to a charity of your choice. I've put a poll up on this channel as well, so feel free to vote on that. Anyways, let's get to it. So all we need for packages today is NumPy matplotlib for a bit of plotting, and then also the animation library of matplotlib. We're going to make an actual animation, as you know, at the end of this video. So we'll start with a little bit of the theory of what's actually going on with the vibrating plates. It's very simple. I won't get too much into the mathematics, but it's important to understand to some extent what's going on with these vibrations and why you get those particular patterns when the sand vibrates and why the sand moves to those certain locations. So for a vibrating 2D plate, we'll come up with a mathematical model, and we'll let the height at any point on the plate, because the plate is 2D, but it's vibrating, so certain points on the plate will rise, certain plates on the point will fall. And at any point, XY coordinates on the 2D plate, you have the height given by u of xy, so it depends on the position on the plate, and time, so it depends on the time. Of course, over time when the plate vibrates, it oscillates. And so the differential equation governing the motion of this vibrating plate is given by the wave equation. Now, this is true for some plates, and it's the assumption we'll make in this video, and it's true for certain vibrating plates in real life as well, but that's only for certain materials. Other materials actually exhibit a fourth order differential equation. So instead of the Laplacian squared, you actually have the Laplacian to the power of 4, and you get more complicated dynamics of the motion of these plates. But for this video, we're going to stick to a simple model for certain types of 2D plates, and that's that they're modeled by the wave equation. So this is the second derivative in time. This is the Laplacian of u, and c here is the constant you see. That's the wave speed. So as a wave sort of goes on this plate, how fast does it traverse from one point to another, essentially? And so there are things known as eigenmodes of vibration. I'll explain what that means in a second, but they occur when the plate is vibrated at specific frequencies. So you have this plate, and if you can somehow vibrate it, whether that's using a string to sort of create an artificial vibration, or you manually vibrate it, if it gets vibrated at these certain frequencies, f of nm is equal to c over 2 pi, the square root of n squared over lx squared plus m squared over ly squared. This is an equation where lx and ly are the dimensions of the rectangular plate that you're vibrating, and n and m are integers. So you might think, well, what are these? Well, in particular, if you know what the wave speed is of this equation, and you know what Lx and Ly are, the dimensions of your plate, you can put in any value of n and m, integer value there that you want, and you can find all sorts of different frequencies. So for example, n equals 1, m equals 2 will give you one frequency, n equals 7, m equals 4 will give you another, and you can create a list of all these different frequencies that you can vibrate the plate at. And so I said that these are called eigenmodes, and that really means something special here. At these particular special frequencies, you have that u of x, y, t, so the solution to the wave equation is separable. It's equal to capital U of x, y times g of t. So you can separate the function into a position function times a function of time only. And so that means that it's separable. This is sort of an eigenmode. And g of t is just a periodic oscillating function. So usually this is just like sine t. It's just up and down. So what it means is that all the points on the plate are vibrating at the same sort of frequency, g of t. There's no waves traversing. They're all sort of moving up and down together, right? Because g of t tells you how much up or how much down it is. And u of xy, for any point on the plate, xy, it tells you the amplitude. So u of xy is like the amplitude, a spatially dependent amplitude. G of t is some oscillating function. And it says that the whole plate is oscillating together, some plates higher than others. And that's sort of what an eigenmode means here. And again, that only occurs when you vibrate the plate at these particular frequencies. So what happens is if the plate is suspended in the center, maybe the plate is resting on a pole that's at the center and that location can't move, but we're vibrating the rest of the plate, then the boundary conditions are such that the maximum amplitude of vibration occurs at the outer boundaries of the plate. And you can show that u of xy is equal to the magnitude of this relationship here. And if you plug in x is equal to lx over 2, or y is equal to ly over 2, remember that if you're dealing with coordinate 0 at the center, the right-hand side is lx over 2, the left-hand side is a distance lx over 2 from the center, and there's a caveat, and that's that n and m, the integers from before, they can only be odd integers. So let's actually code this up. First, we'll get the coordinates of the rectangular grid. I'm going to say x and y, which are the x and y coordinates, of course, are just from -1 to 1. We'll deal with 1,000 points, and we'll create a mesh grid out of those variables here. So here I have x and y. They're just, of course, arrays as you would expect. And then I have my mesh grid as follows to create this two-dimensional grid. If you don't know what a mesh grid is, I would highly recommend checking out my video on mesh grids. I'll put a link in the upper right so you can click on that. But essentially, we can use mesh grids to generate the 2D amplitude function here and plot it as an image. So here's the amplitude function. Of course, here x and y are dimensionless, so I don't include the lx and ly in the denominator. But it's just an amplitude function that takes in the mesh grid and then also the odd integers n and m. And so I can find that as follows. Then what I'm able to do is actually plot this amplitude u of xy for different values of n and m. So for example, here's a plot where n is equal to 3 and m is equal to 5. I can change this to 7, for example, and I get a different plot like this. I could change this to 5. Remember, they're always odd integers. And I get different patterns here of the modes of oscillation. What that means is that at the center, remember this is suspended, so there's a pole. You can think of my 2D plate suspended with a pole at the center, and it's rectangular. And so it's not going to vibrate here. It's also not going to vibrate on these purple lines here or here or here. But these locations where you see this yellow value here, which corresponds to a higher amplitude, it's going to be oscillating most at these locations. And the main thing, of course, is that everything is oscillating together. So this is oscillating higher than, for example, this dimmer value here, but they're all oscillating in unison. So we have this picture of our oscillating rectangular grid. The question is, how are we going to simulate sand moving around on the grid? Well, the idea is that you place a bunch of random grains of sand on the grid, and the plate is going to oscillate up and down. Now, at locations where the plate isn't oscillating at all, the sand isn't going to move, right? There's nothing forcing it to move, so it's going to stay steady. But at locations where there's a high amplitude, the sand is going to move a larger amount. And so you might say, well, what direction is it going to move? Is it going to move here? Is it going to move here? Is it going to move here? What we'll do is we'll choose a random direction for the sand to move. So every piece of sand, no matter where it is on the grid, it's going to move in a random direction, of course, theta, for example. So there's no preferred direction that it's going to move. But at locations where it's a higher amplitude of oscillation of these little things here, the sand is going to move a larger distance. So the larger that the amplitude is at that location on the plate, the more the sand is going to move. And we'll do it over and over and over again, right? We'll move it once, then the sand will all be in different locations. Then you move it according to that amplitude, and it moves and it moves and it moves and it moves. And what you'll find is that the sand in these locations that tends to move a lot are going to rest in these purple locations, and you'll get the sand sort of moving into these locations where the plate isn't oscillating at all. So we can create the coordinates of the grains of sand as follows. This is a really easy way to do it. The locations are from -1 to 1. Right? And the size is going to be 2 by 1,000. So what that means is that there's two coordinates, x and y, and there's going to be 1,000 different points, right? And so if I look at P here, you can see that I have a bunch of different x locations. So this is the x and y coordinates of the first grain of sand, the x and y coordinates of the second grain of sand, the x and y coordinates of the third grain of sand, all the way up to 1,000 different grains of sand, with the final coordinates being x is equal to this and y is equal to that. We can then, of course, plot these on the grid. By the way, this is a little trick here. If I look at the shape of my array, always good habit to do, it's 2 by 1,000. So if I include this little star here, it takes the first, not at the end, at the beginning. What it does is it takes the first dimension of the array, which is 2, and it will separate it into a bunch of different arrays. So what it's going to do is it's going to take this array, it's 2 by 1,000, and it's going to separate the first dimension into different arguments that are passed to the function. So the first argument passed to the function, which is always x, is going to be the 1,000 x points here. And the second argument is going to be the 1,000 y points here. That's what the star does when you plug an array into a function. It separates the first axis of that array into a bunch of different arguments. So I can plot that, scatter these, and you see that these are the locations of all the different points. And then the plate's going to vibrate, and the sand in the locations where the plate is vibrating the most is going to move the most. So because we're doing a Monte Carlo simulation here, I'm going to make use of object-oriented programming to make what we're doing a little bit easier. So I'm actually going to define a sand class, or an object. And so I'll define it below here. And what this class is going to include is the number of points. I'm going to call that n points. So for example, here I have 1,000 different points of sand, and I can change that at the beginning of my simulation and see how things differ. I'll also include the locations of the points, which I'm going to just call points, which is essentially something like this above. I'm going to define the distance, and I'm going to call it delta, that a grain of sand moves when at a position of maximum amplitude. So for example, I'll define how far sand moves when it's located at the highest oscillating amplitude. And from that, it's just linear interpolation to the fact that the sand doesn't move any distance at all when it's at the minimum amplitude, which are these purple lines here. Then I'll define a function move, which takes all the coordinates of the sand, and when I call the move function on this object, it's going to move all the different grains of sand all at the same time, and I'll show you how to do that. I'm also going to track the previous locations of the sand. So every time I move the sand, the class is also going to keep track of where the sand just was. The reason I'm going to do that is so that I can create smooth animations in a little bit, and you'll see why that helps. The reason I'm going to do that is so you can create smooth animation of the sand moving between points. What you can basically do is look at the previous points and the current points of the sand, and you can use linear interpolation to plot how the sand is moving as it goes between different points, as opposed to just plotting frames of the sand moving every single frame, which looks a little jagged and doesn't give that illusion of sand moving around the plate. So the actual initialization function of this class is easy. I just define the number of points is equal to how many points you pass to it. The points is going to be the same thing that I did above, only now I'm saying that there's this many points. So the number of points that I give into the function is how many grains of sand I'm going to put on the board. Of course, it's random. The amplitude function is equal to the amplitude function that I give it, and then the distance it moves at a position of maximum vibrating amplitude is that variable here. So then I'll actually define the move function of the sand. Each iteration that I move the sand, how does it move? And so that's actually pretty simple. So it's going to take in the amplitude parameters. Remember that the amplitude parameters in this case are just n and m. So the parameters just give us what mode of oscillation we're vibrating in. So that way during the simulation, we can actually change the amplitude parameters each time you move, and you can see how the sand moves into the different eigenmodes of oscillation. So my angles are going to be random. Remember I said that each grain of sand is going to move randomly in a 0 to 2 pi direction on the plate. And so for that, I create uniform random variables between 0 and 2 pi, where the size is just equal to the number of points, the number of grains of sand on the board. Then I'm going to create the vector delta r. So if I take my initial position r and I add delta r, I get the new positions of my points. So delta r specifies how the grains of sand move. For that, I'm going to first take the distance that they move at maximum amplitude, that's self.delta. I'm going to multiply by the unit vector here. So remember that there's 1,000 different angles. So this array here is going to be 1,000 different cosines, which are the x directions, and 1,000 different sines, which specify the y directions. So this is a 2 by 1,000 array because this array is size 1,000. And I'm going to multiply by the amplitude at that given location. So the amplitude takes in the points that I'm located at. So there's all the different points. They all have different xy coordinates. And it's going to take in the amplitude parameters, which in this case is just n and m, which are specify the frequency of oscillation. I divide by 2 because the maximum amplitude of this function here, you can show that it's equal to 2. So I normalize so that it's equal to 1. And then when I take self.delta times this, the maximum distance something will move at max amplitude is just delta, because this is, of course, maximized at 2. So I have my distance, I have my direction, and then I have that it's scaled by the amplitude of its location on the vibrating plate. Before I move all the points, I then define the previous points as follows. I copy the original points, and then I update the points. I say self.points equals themselves plus delta r. So they're all moving around. So then it's really easy to run the simulation now that I have this class. I'll first create an ensemble, and I'm going to only include 20 grains of sand. I'll use the amplitude function, which I defined above here. It's got the same name, amplitude. And I'll move them a distance of delta is equal to 0.5. Remember, that's at maximum amplitude. So the whole grid goes from -1 to 1, so it's a distance of 2. If it's at a position of maximum amplitude, it's going to move 0.5. So that's just worth thinking about. So I'll define the class, and then I'll create the ensemble, and I can move this ensemble. So remember, the move function takes in the parameters of the amplitude function, which are n and m here. And so I can move it corresponding to this eigenmode of n equals 3 and m equals 5. So let's move the points, and then I can plot the points. So remember, ensemble.points, if I just look at this attribute of the class, it should be, and I look at the shape of it because it's an array, it's 2 by 20. So there are these are the coordinates, x and y, and there are 20 different grains of sand. And so I'll do the same thing I did above. I'll use star ensemble.points. So it'll take this and it'll give the first 20 points as the first argument, and then the second 20 points, or the y coordinates, as the second argument. I'm just going to plot them as points, and I'll use a marker size of 5. And so I can do this, and I can look at the position of all the grains of sand on the board. And remember that this corresponds to the plate before. So the whole thing is vibrating. Then I can move the grains of sand, right? And I can plot it again. And you can see that the locations will change. And I can move it yet again. So what I claim is that after enough time, those grains of sand will settle into the positions where the plate isn't oscillating at all, which of course on this plot here is the purple regions. So let me show that. So now I'm going to create an ensemble of 10,000 grains of sand, and they're going to move only 0.05 distance each time I run the move function. So here's my ensemble, and I can plot them initially, and you see that it's all essentially random. This for loop will move the grain of sand 10 times. So here I'm using n equals 1 and m equals 3. I'll move them 10 times, and I can plot it. Okay, they've moved around a little bit. You don't really see any pattern yet. I can do this again. Plot it. Okay, I still don't really see anything. And I'll do this a few more times. And you can see they're starting to settle into a certain mode here. You can start to see lines form. And now if I move it 100 times, say, okay, now you start to see a pattern forming. Let me move it 1,000 times. And now you really start to see the first eigenmode of vibration. So what it means is that at these locations here, you have the most vibration. And at the center location here, you have less vibration. That's why the grains of sand are settling there. And of course, I can run this one more time, and you'll really see that there are very few points in these regions where the vibration is occurring most. So now what we'll do is we'll create an animation of what's going on with the sand. And so, of course, an animation consists of a sequence of frames, right? Maybe 25 frames per second. Each frame shows something different. And so we'll set it up as follows. Every 5 frames, we're going to move the sand points, right? We're going to call the move function, and the sand points are going to move. And if I were to just plot an animation of the sand move, 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 it would look really jittery. The sand would look like it's not moving between its initial location to the final location. That's why I defined the previous points inside the class. So what I'll do is in between those 5 frames, we're going to use linear interpolation to get the position as the sand is moving between those locations. So I call the move function. I'm not going to do 1 frame, initial position, next frame, the next position. I'm going to just do first frame, initial position. I'll get the next position, and I'll do 5 frames to have the sand move between those locations. And you'll see what I mean here. So here I'm just creating a axis. I'm setting up everything I need for the animation that I'm going to plot on. The background's going to be black. The sand, pebbles, or whatever are going to be white. I'll turn off the axes, and then here's my animation function. So I is the frame, and when I animate, I say, okay, I want 500 frames total. So it's going to call this function 500 times, and what's going to be drawn on that animation is specified by the integer I. So if I modulo 5 equals 0, what that means is if I divide the frame number by 5, and that equals 0, so if it's a multiple of 5, then if I is less than the 250th frame, I'm going to move it, and I'm going to change these to be odd integers. I'm going to move it according to this mode of vibration, and then after the 250th frame, the mode of vibration is going to change, right? So maybe then the plate is perturbed at a different frequency, and I'm going to move it according to this mode of vibration. So the important thing to note here is that it's only every 5th frame am I going to move the points. So then in the in-between frames, I'll draw my points like this, and you might think, well, what the heck is this equation? It's my previous points plus whatever the heck this is times whatever the heck this is. And so I'll explain this equation as follows. When I is divisible by 5, so 240, 245, 250, this whole thing is equal to 0 because there's no remainder, and I'm starting at my initial points. Then as I moves up a frame, so say I go from frame 240 to 241, well, 241 modulo 5 is equal to 1, so I'm at 1/5 times my points minus my previous points. Then as 242, this is 2 divided by 5, so that's 0.4. 243, well, that's 3 divided by 5, so 0.6, then 0.8. So what I'm doing is I'm slowly going from my previous points, becoming closer and closer to my new points. And that's essentially a linear interpolation, which will have the points move smoothly between their initial points at the frames 240, 245, 250, to their final points as you go through those 5 frames. So here I'm creating my ensemble. I'm going to have 10,000 points using the amplitude function. It's going to move this distance every time. I'm going to create an animation using the animate function that I've defined above. I'm going to draw it for 500 frames, and when I save the animation, I'm going to save it at 25 frames per second with a resolution of 200 dpi. So here I'm actually showing the animation of what's going on. So you can see over time the sand tends to move to the first eigenmode. So remember, this is the locations where the sand or where the plate is not vibrating. Then it switches to a different eigenmode and the sand will switch to different positions. Of course, the locations of maximum amplitude is where you don't expect the sand because it's pushing it outwards. So it looks kind of nice. Like you can sort of watch this for a while. It's almost meditative. Anyways, I hope you enjoyed this video. If you did, please be sure to like and subscribe. Check out the merch as well. And I'll see you next time.